Hi, everyone. So today I'm going to be talking about a project that we've been doing for a fair amount of time at this point, investigating neural responses using fast non-selective MRI. So this is not layers. It's not even remotely close to layers, not even imaging. So just if anybody wants to leave. But it's a pretty interesting sequence that we've been trying to work with. So just to start.
Hey, Tyler, can you get rid of that?
Yep.
Sidebar.
Yes, I can get rid of that.
Thank you.
Is that better?
Yeah.
Okay, so the basic question that we're taking on in this project is, can MRI record neural signals directly? Hemodynamic fMRI has proven extremely useful for non-invasive measurements, and it's very obvious in this building and in a lot of buildings that it's made a lot of progress on measuring human brain activity. But the potential of replacing that with the potential of replacing blood-based measurements with direct neuronal measurements promises a lot of kind of really big things for us. Temporal resolution is an obvious one. It also gives us a lot more interpretive power if basically most of the things that we are talking about in fMRI are really about brain activity itself, what neurons are doing. And so I should clarify that this is not a new thing. This has existed pretty much as long as the concept of fMRI has existed, but people have tried to investigate it by looking at things like neural current imaging, magnetic source imaging, cell swelling, as well as more recently, there was a lot of hype around the concept of Diana, which was maybe not as specific as any of those, but there was some possibility that it could be related to neural spiking. And I'll just go over that really quickly because it's the most recent of those efforts. So there was a paper in 2022 that came out of the Park Lab that discussed the possibility of actually measuring neuronal activity directly with fMRI. And importantly, it also used a really simple sequence, which I think is part of where the excitement came with this. So basically, they didn't use a crazy contrast or anything like that. They just used a gradient echo sequence, and they went really, really fast as they possibly could. And in addition to this, they also played a few little tricks in the sequence in order to try to increase their resolution even more. And so basically they used what's called the 2D line scanning method. And the 2D line scanning method, just for those that aren't acquainted with it, essentially means that rather than trying to collect a full image and then reconstruct that as an image and then move on to the next one and collect your full image and reconstruct that one, and having TRs kind of in that block or in that manner. And they instead would not reconstruct their data chronologically in how they collected it, but in reference to the stimulation that they cared about. And so what they would do is they would go to line 1 of their K-space image, and then they would just collect line 1 over and over and over again to create a time course of that line. And then on the next trial, they would start over again, and they would go to line 2, and they would collect that over and over and over again. And this allowed them to actually record at 5 millisecond resolution in comparison to the stimulation that they were trying to record. And you can see that it was very exciting to kind of see what these reconstructions looked like. So essentially, when they reconstructed the entire image, it means that like they have this time course for each one, they put them in. The image is the average of all the time of all of those time courses. So there's some limitations on what kind of studies you can do. But they had these responses that are really, really fast, like 25 milliseconds, which is where the idea that maybe it's neural spiking came from. So they were able to sample at 200 hertz, so 5 milliseconds. But importantly, and I alluded to this a little bit, they have this interesting structure, which is that in order to create an image, they need to repeat a trial for every line of case space that they want to go into those final images. And this is really, really demanding. It's really demanding for rodents. It's beyond demanding in humans. It's really hard. And so in this project, we were kind of coming into this pretty early on in this story of trying to figure out and like trying to learn whether we could replicate this. And we took the approach of basically trying to get rid of the images entirely and just try to understand whether you see signal modulations at all with an fMRI sequence. And so what we did was we defined a GRE sequence that had no gradients at all in its encoding. The only gradient that's involved is a spoiling gradient. And importantly, by avoiding recording images, we only have time courses. And this means that we don't have to repeat trials for all the phase encoding lines. Every trial that we record, we can look at kind of as a time course analysis, which is similar to how you might think like EEG is recorded or MEG is recorded. So this is a purely proof of concept study, and it just aims to investigate whether fMRI signals actually carry any neural information. And in follow-ups, we can worry about the possibility of trying to resolve these into images themselves. And just to give a little bit of a background on the sequence that we're looking at, this is really the bulk of it is just an RF and an ADC. So basically we would do a non-selective RF pulse followed by a readout and then followed by a spoiling gradient. That spoiling gradient is designed to produce a 2-pi wrap over the side of over an object the size of the ventricles, which is kind of what we thought would be the most coherent thing at the end of each of our TRs. And then lastly, I'll just say that in order to accomplish RF spoiling, we also had phase jumps, but these were random jumps. They weren't periodic in any way. And the reason that we didn't want them to be periodic is because one of the first things that we saw was that we already had frequency responses when we started to record these signals using kind of the standard tools that are used in MRI. And so oftentimes these kind of go a little bit unnoticed, I think, because you're not recording the same line over and over and over again every single TR, but normally you move on to the next line and you wouldn't know that you're having this kind of like cyclical process. Although Jeff has done some work on this where they actually modeled how to get kind of the best signal over time. What we decided to do was basically just do random jumps in phase, because you can see that in this example here, the blue is the standard on Siemens systems, and basically we were always getting this modulation in our signals that were coming out. And you could change this to other functions, but if it is a function, you'll always get something that comes kind of back out of it, because we're recording so fast that we have many, many TRs. So you're gonna kind of rotate around over and over again. And so with the random one, we still get some peaks you can see going through time, but they're less predictable. And I mean, actually they're really predictable, but they are less likely to kind of interrupt the sequences or the experiments that we're trying to look at. They won't contribute to frequencies that would be mistaken for neural activity. The second thing that we were trying to figure out before we even really got started was there was another paper fairly recently, I should put it in, but essentially they were looking at what they called the Doty effect, which is a dark joke on the Diana sequence, but it was trying to explain the possibilities of why Diana was seeing these really, really fast stimulation responses. And they actually found that there is a small gap in the sequence when you put a trigger in on Bruker systems. And so therefore you were actually interrupting your steady state, and we wanted to test whether this was where some of our stuff was coming from, or whether we could reproduce this kind of externally. And it turned, I mean, Siemens systems don't have the same type of break in them, but in order to test it, we actually artificially placed breaks in order to see what it would do to the signal. And we can produce like really awesome signals, like 10% signal change, if we put in like a 40 microsecond delay right before every trigger, and it'll always happen at the exact same time. What's kind of interesting about this, I'll skip this for just a second, is that they also showed, and we could also show this as well, that you can kind of extinguish these effects if you care very deeply about what the stimulation delays are in your system, which is always kind of a problem for us. We get a trigger out from the scanner, and we normally give that to a computer that has built-in delays. One, because of USB has delays. Two, because screen refresh rates might not be perfect or inline, etc. And so if you keep really good track of these and you use those in your analysis, you can kind of extinguish some of these effects, because suddenly you won't be perfectly in line with the trigger. But if you're perfectly in line with when the stimulus was actually shown, then these average out and smooth out a lot. But either way, that's not an issue for us. We just wanted to make sure that that wasn't something that we were running into. Okay, so what do our signals actually look like? Well, they are all tissues. This is a completely unselective or non-selective type of sequence. So you kind of have everything going on all at once. And you can already kind of see these are all of our channels across one FID decay, which is about 10 milliseconds long. But the beginnings are particularly harmful because one, there's some B1 instability that occurs, but also because there's a lot of fat signals at that point. And fat decays very, very quickly. So we took the approach of essentially just cutting that out, because obviously we don't care dramatically what fat is doing. So at you can see at about 4 milliseconds here, you can see that things become much more stable and you're looking more just like a decay curve. And that's kind of the data that we used, was this 6 milliseconds at the end there. Just going back to this, we did have to kind of keep track of when our stimulation was happening pretty well. This was the genius of Pete, that he put the EEG system next to the MRI system, and that allowed us to actually track kind of all the components of what's happening. So we could keep track of the MRI clock, as well as a photodiode that keeps track of when the stimulus actually comes on. We were also using these at the same time with an EEG system for some of the studies. I'm not showing those data today, but this gives us a very accurate estimation of how much presentation delay is occurring and what TR we're actually looking at as the onset times. So this is kind of a big difference in comparison to a lot of the other studies that have looked at trying to find the Diana signals or direct neuronal signals recently. We took the approach that you can do event-related designs, and we have tried that a bit. They're a bit unstable and they're really hard to replicate. And you've already seen kind of the work that goes into trying to make sure that you can do those things. But another aspect of neuronal signals that we thought was really important and would kind of help resolve whether you can actually see these things with a little bit more power is that neural signals should follow stimulation frequencies. And so what we did was we kind of modulated those frequencies using a sinusoidal checkerboard. So this is basically, we can take a checkerboard and we can have the frequency flip, rather than just being from one end to the other very quickly. We can modulate it as a sinusoid, and we can do this at 1 hertz, we did it at 6 hertz, 10 hertz, and 15 hertz to see how high we could kind of go with that. And this is kind of a nice thing because we were hoping that it makes it very relatable or comparable to a lot of EEG and MEG studies, because this is a pretty common paradigm there.
Can I ask about is this a carrier frequency of the checkerboard, or is the checkerboard kind of on for 1 second, going dark for 1 second? Or is it more Laura Lewis style that's kind of flickering once?
No, we initially tried to do it in the Laura Lewis style, and to a certain extent we could do it. The problem is that the carrier frequency and the frequency of the actual flicker start to beat once you go away from very low frequencies, because she was looking at like 0.25, 0.5, and 1 was the highest that she ever went to. 1 was our slowest one. And there you can do it. But once you go to 6, 10, and 15, it becomes really hard to see at all. And so you don't really know what those frequencies are. Not to mention that PsychoPy doesn't always do exactly what you tell it to do, which is fun. Pete and I were down at the scanner measuring some of that yesterday that I can mention. PsychoPy can carry all of these frequencies just fine. It's just not a pure sinusoid. It's kind of like it looks like a ramp. So basically it'll do this and then it'll jump like very, very quickly as it goes back up. Particularly on fast frequencies. On those slow frequencies, it does what it says it should.
Tyler, quick question. Have you calibrated the projector carefully? Because that will affect the waveform.
Which type of calibration do you have in mind? Like you're talking about like
Linearizing the
luminance?
Luminance.
So we have taken into account the calibration that is already done on the VPIC system. But at the same time, I think that there's probably more to do. Maybe you and I can talk about that, because I would be curious about what temporal aspects you're thinking about it would affect.
Well, you have a sinusoidal luminance change, right?
Yeah,
So you're putting in a sinusoid, but that's not what you're getting out. That's not
Yeah.
what the monitor is going to produce. Unless you have a calibration table.
okay. Yeah, let's talk about that then, because that was one of the things that we were kind of curious about, and that's why we were measuring it yesterday, but we were doing this off of the photodiode cells, rather than off of the VPIX itself.
Still, I think you want a calibration table to
So,
relate.
so let me just understand this. So how much off would it be without a calibration table?
So it's going to vary display by display. It's going to vary depending on how long the display has been on for. Like it will warm up and change over time.
I know, but
It
how
should.
much- I'm just trying to figure out if, all we're looking for is anything that happens that's remotely correlated with the frequency. We're not,
Right.
we're
If
not,
it's a temporal frequency, I'm not concerned, but you have an image of a sinusoidal input. That's not actually what you're inputting. That's my only point.
no, I know it's probably not. I'm just trying to get a sense of if it's different enough such that the results are uninterpretable, or is it different enough that it doesn't really make a big difference? I mean,
Since you care about the time, temporal frequency, it probably doesn't matter much. But if having a sinusoidal modulation matters,
no, that doesn't.
then
I mean,
then
it could be a sawtooth, it could be anything. We just want to see something that looks like has some elements of the frequency. I mean, we're at the very
temporal frequency, yeah,
Yeah.
then it's fine.
Yeah, I should clarify, and maybe I didn't say that correctly, but this image that you see here, that's the stimulus. It wasn't a sinusoidal checkerboard in spatial dimensions, it was sinusoidal and temporal.
Right, but black becomes white and white becomes black.
Yeah,
Not counterphase. In other words,
sorry, say that
it
again?
goes through gray scale before it changes.
Yeah, it does,
Yeah.
yeah.
Right. So,
Yeah, we can talk about that more. I would be really curious about the calibration. I mean, maybe it's something that we should be doing on that system anyway. for
so we
people.
have, yeah, we have a very high quality photometer in the lab that will measure luminance output. So we can just measure this and get an answer.
And we did that.
But-
So we specifically had a photodiode made to do this that we also use in the EEG. So that's what we actually tested yesterday, which is we have these frequency changes mapped out.
No, it's not the temporal frequency. The photodiode will tell you on periods. I'm talking about the luminance in the monitor.
This is calibrated for luminance. It gives us a waveform that comes out.
I can't imagine that's accurate. Anyway, we can, I'm totally sure you can get the temporal component of the photodiode. But I would be surprised if you can get accurate luminance measurements.
I also think that
Yeah.
Eli's referring to measuring it after it's gone through the projector, not what we see on the stimulus presentation computer.
Yeah, and that's fair. That also brings up, the complaints that we've had on VGA input and various other things that we can talk about offline.
So yeah, definitely, we should put I mean, I imagine you could easily put the photodiode on the back projection screen, right?
Yeah, it's MR conditional,
Yeah.
so we can do it.
So I honestly don't, I mean, I think that for certain experiments, it's critical. For this one, my hunch is that it's not.
I agree because it's the temporal component that you care about.
Yeah, yeah.
A quick point, if the temporal component is the only important thing, instead of working on discrete frequencies, sweeping a frequency from a range from 1 Hertz to 15 Hertz continuously will give you more flexibility to detection. Because there might be like frequencies could be carried to other frequency domain for any reason. But if you sweep it, you will just eliminate those problems. Like sweeping 1 Hertz to 15 Hertz in a given time would give you
So
more power of modulation. If you're modulating based on frequency, the Diana sequence, I think sweeping will be more powerful instead of.
So you're thinking that the analysis would then be like a spectrogram where you're viewing it going through the frequencies,
Yes.
or?
Yes, because
I see.
also I feel it is probably sensitive to different frequencies differently. The amplitude of the modulation will transfer differently. I assume 15 Hertz is less sensitive than 8 Hertz. 8 Hertz, I believe 7.8 Hertz is maximum. So there will be a curve there too. So if you sweep, probably you will have more modulation in the Diana sequence. That's what I feel like. Yeah.
That's a really interesting suggestion. I don't think, I had never thought about that. I'm not sure if any of us had.
Can I make one more point? A minute ago, I said that the calibration doesn't matter if you care about the temporal frequency. That actually is not true. Because if it was a sawtooth, you'd have harmonics at other frequencies.
Yeah.
Right? The whole point of having a sinusoid is you want to concentrate it at one frequency. Right? So if it's not calibrated, you don't have a sinusoid.
Yeah, let's talk about the calibration offline, because I'm do you have a VPIX calibrator?
We do up here. And I have a $10,000 photometer. And it takes us all night to calibrate. It's not a trivial, just stick a photodiode on the screen and measure it.
But I'm assuming it's not MR safe photo system.
No, but it's got a pretty powerful lens and we can set it up outside.
Okay, yeah, let's discuss that.
Yeah, we can also
more.
we have graphics cards that can do 10-bit calibration, so we can get very fine contrast increments.
Sounds great. Yeah, that would be really helpful. Okay, so then on to the types of analysis that we were doing. We've tried quite a few different things. I tried looking at spectrograms. They tended to be pretty delicate, depending on how much data was involved and the type of data that was involved. In the end, what we've kind of settled on is the idea of using, there was a recent paper in Imaging Neuroscience that talked about using short time Fourier transforms on EEG data. And essentially what they would do, I can point it out here. So if you have your continuous EEG data here, you would block it into what are essentially Welch windows for them, but they're like 2-second periods that jump by 1 second, and they just keep going down. Each of these is shown kind of here, and then they're taking a Fourier transform of this short time in order to get the frequencies out at a resolution that they can still analyze in more of an fMRI GLM type of way. And so basically they've reduced their EEG temporal resolution to about 1 second. But they get the frequencies out as a benefit. So each of those 1 seconds has a set of frequencies that are associated with them. And then they can define what conditions are happening. In our case, it's our blocks of stimulation. And they can actually look at what are the changes that are associated, what are the changes to the frequency response that are associated with a particular stimulus being on. And what this actually looks like for us, these are across 4 different channels that are all in visual cortex. And I've marked both the primary frequency and the first harmonic of each of the stimuli that are on the screen at the time. There are a couple things that I think are kind of interesting. One, the 1 hertz stimulation tends to have it a little bit higher than a lot of the other ones. A lot of the other stimulus presentations actually have like a pretty big reduction in the low frequencies that are associated with them. The other thing is,
What are the colors?
each of those is a channel that's associated with visual cortex. I could have combined them, but for the time being, I'm just looking at them separately. Biowolf went down, but normally I try to plot these also with like M&E plots, so you can see where in the head you're seeing frequency responses, etc. We do tend to see the 6 hertz stimulus often kind of has a little bit of a bump around its first harmonic, and this is not just in these channels, this is often in a lot of the channels. But overall, you can see that this is across 40 different runs. So this is 10 subjects who are doing 4 runs each of 10 minutes. So this is a lot of data that we have in here, and our t-values are not very high, which basically means that if we're seeing responses, the responses are very weak at best.
Tyler,
Yeah.
I don't know, I was renewing certificates, so I popped in a little bit late, but what I wanted to ask you about this figure, which puzzles me, is that why are there no kind of peaks in the frequency distribution? You should have, if you have energy at a dominant frequency, you should have like a peak around your main frequency, and you don't see that.
Yeah, I mean that's exactly what you would want to see as a strong result. But yeah, we don't tend to see that very well.
So
And-
Tyler, I'm a little
Mhm.
confused. How does this look when you do like the same analysis with EEG?
Like there's a very strong frequency response at that particular frequency.
Okay.
And in EEG, it's always at the first harmonic.
So do you have that data? I mean, I'm kind of curious.
Not at the moment, no.
Okay. In terms of plotting t-value,
Mhm.
I mean, is there any way of just, I mean, t-value, I mean, I'm not even sure how one would calculate t-value and if we even know the best way to calculate the t-value. But
What do you mean?
like, assuming the noise structure, I mean, what is it against? Is it like point by point? Or is it like
Yeah,
frequency
so
bin by? Right.
it's a test across the 40 runs that is in comparison to the baseline. So this is changes from the baseline frequency response that happen consistently or not.
Okay,
And so if you had just zeros, that would mean that there's no change to the frequency response at all during the stimulus. And if you ever see anything that's significant, that would mean that that is a significant change across every subject, etc.
okay. Okay, I mean,
And the reason that we went for the t-value comparison here is partially because the scale of the frequency responses across different individuals is pretty dramatically different. Some people just have all large ones, some people have all small ones, and so incorporating this into the GLM was how to try to overcome this. I think it's also part of why looking at the spectrogram approach is relatively unstable, is because it's hard to compare different subjects to one another. Although over the last few days I've been thinking about whether it's best to just kind of normalize to some frequency that we think is completely uninvolved, like a high frequency or something like that, and basically just say like we're scaling everything in comparison to that. But it's an
because like these results, I mean, this looks like obviously, this clearly, I'm not trying to figure out the best way to show it, but I feel like,
Mhm.
This is pretty much a null result.
Yeah, I
Tyler,
would say so.
I think what you need is a frequency sweep, because like the problem is here, like if you have a noisy measurement and if you're stick on the certain frequency, of course it's going to be different in every subject slightly in the frequency domain. And then you're like pulling now 40 runs from 10 subjects and they're not aligned in frequency domain. You're doing point by point statistics here. So you can benefit a lot from frequency sweep. Just sweep from 6 hertz to 12 hertz, and you have a certain frequency range, and it is more robust to noise because it's a frequency range instead of single frequency.
I'm a little bit confused about that, and maybe you can explain more. So what you're saying is that we show a 6 hertz stimulation.
Yes, and it's gonna sweep. It's gonna slowly ramp up to 12 hertz, so you're stimulating a range of frequencies.
Would that result in power at the rate at which the frequencies change? I'm a little bit confused about what that would look like.
No, flickering rate is changing. It's getting faster.
I know, but the power spectrum would then have power at the rate of frequency change rather than the frequencies themselves.
Yes, clearly. I mean, you can sweep from 6 hertz to 12 hertz, which is the most dominant part expected in the literature.
Yes.
And you, instead of looking here 1 point, you have a lot of points in the spectrum to compare.
Right, but let's say that sweep takes, I don't know, 5 seconds?
A minute. I think it needs to be
minute?
long. Or I don't know. I mean,
So then
how do
do
you
you look
measure
at
it?
the power spectrum at that frequency?
Yes.
At the frequency of the sweep?
No. So the main point here is that in order to average narrow band frequencies with slight variations across subjects, then by doing a sweep, you're going to have energy that is spread along a range of frequencies. So it's a way of inducing a way of aligning them more efficiently. You see?
So you're adding some slop to the spectrogram, so they're more likely to average.
Exactly. I mean, you might have a subject variance across.
Why not smooth the amplitude spectra?
That's another way. I mean, that may work too.
Right? They're independent at different frequency.
That's a possibility. That's what I want.
Exactly.
It's possible to do that, but there are advantages in sweeping because you have a broader range of energy and a broader range of neural filters responding to that energy. And because you have the relative ranking of how the frequencies are changing, you have a very rich additional source of information to pull out.
So I would like to understand this a little bit better. So you're saying that the analysis on a frequency sweep would basically be like, if you had a 2D spectrogram where you have time and frequency response, you would see kind of it moving across. Or
yeah, I
or
mean,
is this not correct?
The well-known is that the well-known is a chirp signal. It starts with the frequency and dampens down, but doesn't need necessarily be like that. I mean, if we know the sensitivity of the field, in this case visual, you can sweep in all domain. I mean, it could be 4 hertz to 12 hertz or 16 hertz. I
Yeah,
don't know
I
what exactly
wasn't-
range.
I wasn't confused about what the stimulus would look like. I'm trying to understand what the analysis would look like. So you're saying you would look at changes of frequency response over time?
Yes, I guess so. So it's
But-
you look, it's just, you have a sliding window. You can make a sliding window in narrower steps, and then you have a clear idea about how the power distribution should shift across time if you have a chirp.
I don't
So
really
once you have-
understand. I don't really understand how your sensitivity will improve.
I don't either.
If you just put all the energy at what a well-responding frequency, then the advantage is that you don't have to look at all the other noise bins, right? If you look at just 6 hertz, for example, you have only noise in the 6 hertz bin bandwidth, and you don't have the noise from all the other bins. So I think there is no clear advantage to use other frequencies. Putting all your energy at a good neural frequency, I think that is a fine approach. I don't see anything wrong with that.
It would be fine to smooth the spectrograms before averaging across subjects, right?
Why
If-
would the different subjects be different? 6 hertz is 6 hertz, right? It should be all at 6 hertz, and it all adds together.
I agree that, but I thought the conversation started from the assumption that there was a variability across subjects. Now, having said that, it is.
Why would that be? Why
I
would
have no
that be?
idea. I agree with.
That's just doesn't make any sense.
I possibly agree with that too, but I was starting from the assumption that they said that there was variability across subjects. So if that's the case, then
Yeah.
Yeah,
No,
but if
that-
the response is slightly broadband and the noise is independent across frequencies, smoothing would help.
but you have a narrow band signal where we should have a broad one response.
Because neurons have different onset profiles. And the EEG is broadband. It's not at
Well,
one.
the EEG looks, I mean, if you did one frequency at EEG, the EEG results look great.
Really, just
Yeah.
one peak.
Yeah.
I mean,
Yeah,
I mean, there's
definitely.
probably harmonics, but, you know,
it's
but
not
still.
a spike, but it's
Yeah.
pretty narrow. So like if we were to look at it as a spectrogram, let's say we take the 15 hertz stimulation at 30 hertz and maybe like a side lobe of, let's say, 3 hertz on each side, there's a dark band that like it's a very, very clear response, which is I think what most of us are used to in like carrier frequency responses. But this, we don't see anything nearly that strong in the fMRI signals.
Yeah, and all the subjects should be the same, right? Maybe the width of the response will change, but they will be all centered around 6 hertz. So just looking at 6 hertz, averaging at 6 hertz should be just fine.
Yeah, so I should also clarify that I wasn't suggesting that there was a frequency change from subject to subject. I just noticed that there's a lot of difference in the amount of signal, bulk signal that we get and the amount of noise that we get. And so that was what I was trying to figure out how to normalize.
Yeah,
So one comment about that scrambling, that random scrambling, I don't really see the advantage. So you said then you don't get noise at the peak of your stimulation, but that's not true. If you do random scrambling, then the noise will be everywhere, and it will be a big mess. I think if you do quadratic phase scrambling, you get a minimum amount of background noise, and it won't be at a specific peak. It will be distributed at a low level. That's why all the scanner manufacturers use quadratic phase scrambling.
Let me go back to that slide. You're talking, so
I've got to log off.
this
Bye,
one is
Tyler.
quadratic. I'm kind of, so when we see it, we often see these like periodic effects. And
Yeah, but so you should optimize the scrambling scheme based on the conditions. So based on the TR and the
Mhm.
prevalent T2s in the sample. So just copying whatever. So that 50 and the 117 from GE, they're optimized for in vivo scanning at TRs that are on the order of whatever, 30 milliseconds or so. But if you're going to scan much faster, then you have to optimize that scrambling scheme. So you have to change the phase increment, and 50 won't do that.
Yeah, you and I discussed this a little bit quite a while ago, and I am a little bit. So under most circumstances, I would say that that makes a lot of sense, but when you have all the tissues, you can't choose a T2 that makes sense necessarily. So
Well, the minimum T2 will be maybe 60 milliseconds at 7T, and at 3T maybe 80 milliseconds, right? So, and the TR is way shorter than that. And based on the ratio of the two, you can select your phase scrambling scheme. What was your TR?
10 milliseconds.
10 milliseconds.
Yeah.
Yeah, that maybe, yeah, then maybe I wouldn't use 50, but maybe 47 or so.
Yeah, we can simulate those. But maybe I can follow up. So
So if you take the frequency spectrum of that, then whatever peaks you'll find, they will be at certain very predictable frequencies. Whereas with the random, they're going to be all over the place, right? And I think
that was
it's
the
harder to
idea.
interpret if you do random, and I think also the energy is higher with a random scheme. The noise
Overall,
energy.
you mean?
Yes.
That's what I was wondering. Can you just ignore that frequency in there?
Yeah, so one of the things that we found, I mean, when you look at it in the Fourier or in the power spectrum, there are a whole bunch of peaks. And so yes, you could definitely design a quadratic of a particular increment in order to fit in between all of the stimuli that you wanted, including the harmonics. It just seemed much easier in this particular case to reduce all of the frequencies in the signal and deal with the fact that, yes, we were aware that it was adding noise. But that we wouldn't have to worry about that as being like, oh, we accidentally hit this exactly.
Well, no, the peaks will be everywhere, right? So you could be unlucky and have a peak at your stimulation frequency.
Yeah, I suppose that's true. That's pretty much what I had. Are there other questions or comments? They're very welcome.
Yeah, I think that I mean, obviously this is, I mean, these results look like no results, but I think that if you, for instance, if you tried to plot like, I mean, energy under the power spectrum at the various frequencies when you change the frequencies and see if it modulated with the changes frequencies in some systematic way, like, it's high and then it's low and low. And then, if there's other ways of extracting the data such that it's cleaner, because I feel like you're somehow putting it in such a way where everything looks like it's sort of, I mean, even like the high frequency stuff looks like, it sort of reaches significance, and I don't know what that means. I don't know if it's noise. I don't know if it's part of the signal. It just seems that you started with a clean way of displaying it that seemed convincing, but obviously if it's not statistically significant, it isn't. But I think that there's sometimes you're putting things in a way like doing the point by point comparison at each frequency seems like it's you're not leveraging like the experimental modulation as much as you could to pull out the signal. I could be wrong, but
No, that makes sense. I mean, I had thought about what's the best way to do individual tests in between them, because really what you do care about is, I mean, you would like to know that there's a change from baseline at a particular frequency, but you also really want to know when you show a 6 hertz stimulus, it is different than a 10 hertz stimulus.
right.
So yeah, we can look at that.
And different in some statistically significant way. Yeah, I mean, I think that, I mean, backing up way, you know, in the last fall, when you showed me those ERP-like plots, that looked very significant. I mean, it looked significant. Obviously, there's no tests, but those traces looked like EEG traces. And now going to this, it seems like, oh, that's I would think that those traces would look much noisier, should look much noisier, you know, given what you show here. I'm just trying to get my head around this, about the nature of the noise and the nature of, you know, the
Sure.
signal, how you're trying to capture it in a way that, you know, convinces everyone.
Yeah, no, that makes sense. Yeah. It's interesting with the event-related designs, there were some that looked convincing and we thought they were really interesting. They were like 600 trials per subject, which is a pretty insane amount, and those plots never really showed the noise around those responses. But yeah, I think combined we can try to make a story out of it. That's true.
Yeah. I mean, you know, but if you're, obviously it comes down to, if you think there's nothing there, then there's nothing there. And you know, and if you think there's something there, try to show it in the most convincing way.
Sure.
That's statistically, you know, valid.
Did you try to look at the cardiac frequencies and see if they could disturb your analysis, or?
So in the results that I'm showing, we do have a Butterworth filter that is taking the cardiac and the breathing cycle out. I can try not removing those, but yeah,
but
it's
how do you take it out?
by temporal filtering, which it kind of hurts us a little bit because obviously the 1 hertz stimulation is very close to people's cardiac response.
Do you do a frequency filtering, or how do you take it out?
Yeah, it's frequency filtering. Yeah.
Because so the systole is a narrow peak, right? It's like maybe 100 milliseconds wide. So there is a lot of harmonics up to 10 hertz or so, I think.
Mhm.
So that some of those overlap on your stimulus frequencies. So what
Good
you could,
point.
maybe based on the pulse oximeter trace, you can filter those cardiac signals out,
Mhm.
or reorder the data based on the cardiac phase and get rid of cardiac noise that way. I don't know how big cardiac noise is if you do no localization, so you get the full signal. Maybe it's not a big deal, but it's maybe worth checking.
No, that's a good idea. And we do have cardiac and breathing traces on all of these data. So
Now, I have one question. So if
Sure.
all this would have worked, why would this be exciting? It's not clear to me. Like, is it like better than EEG or MEG? Like, what is, if this would have worked, you know?
Well, I mean, as I said in the beginning, it's proof of principle. Like you have to know whether the signal can actually carry these frequencies in the first place. But if you know that it's there, you can try to devise imaging schemes for it. And then, yes, it's better than EEG to know that you can do MRI pictures of EEG responses.
Okay,
How
I
you
see.
do that is an open question, but
Yeah, there was a way to go for doing like imaging actually with it, if this would have worked. I see. Okay.
Yeah, I mean,
yeah,
just try to
that would
see,
be ideal.
I mean, we're just trying to see anything, you know,
Yeah.
and no, I mean, there's no way this would be like practical. We're just trying to, you know, be able to show, you know, because no one's been able to show really convincingly that neural currents exist. And so we're just trying another way and that we think is more sensitive.
Well, the neural currents exist. It's just that you can
Right.
measure.
Right. The neural currents exist, but they're probably about an order of magnitude. The effect is too small to see in MRI. So, or yeah.
Would it be beneficial in any way to, instead of doing non-selective and taking the signal from the whole brain, from doing selective and only taking signal from, you know, the occipital lobes, or like, you know, narrowing down where the signal's coming from, some, or introducing those
Yeah, that I think
gradients somehow affect things?
it's a very good idea. I think doing the exact same thing, not doing any encoding, but just doing a slice profile could potentially help you a lot. Also, it's kind of an interesting question. It's not something that we've gotten into just because you can very, very quickly complicate things and move into kind of a different question, but you could potentially further isolate occipital cortex by just the fact that, like, if you have a slice profile that's kind of doing this, you know the channels that are actually occipital. You're not getting them from up here. So yeah, you do have kind of sensitivity encoding, you just don't have any frequency encoding.
Oh, so when you said channels, you meant the receive?
Yeah.
Coil channels? That makes sense, okay.
Yeah, sorry if I didn't make that clear. Yeah, Farouk, we have a 32 channel, $7 million EEG system that we're trying to build.
So you could also do a readout gradient, right? That wouldn't affect your temporal resolution at all.
It's true. I also thought about this a little bit, and especially if you did do something like, no, it's a very good point. Actually, I had considered the case that Joel had just mentioned, that you would do something like a slice profile and then just do a single line scan through it over and over again. That would give you the encoding as well. But I think you're suggesting a non-selective pulse, and then you're basically just saying, is it anterior or posterior kind of thing. You could just do the readout like this.
Yeah, or with the selective pulse, right? Then you only miss the phase encode.
Yeah, exactly. It's a good point. And we have that sequence. We could definitely try it, because with the line scanning sequence that we have, we could just not turn on the saturation pulses, and then you'd have the readout. And it would be very fast because it doesn't have saturation pulses.
So at the beginning, you used echoes as a measure of whether it's boat-like or not boat-like, which is what you didn't really take advantage of now.
Yeah,
that was the idea by too.
So the reason that it's not in this particular analysis is because it's kind of one added level of noise, because you can have noise on your estimation as well. And the hope was always that it would clean it up, and maybe we can get there. Peter also suggested having a slightly longer TR, which we have some data recorded with 25 millisecond TR rather than a 10 millisecond TR, and that allows us to like kind of have a little bit more isolated fold at the end. So
yeah, I mean, one of the quick just idea with the power spectra, I mean, and maybe this is the same thing, but did you take like a fit to the whole power spectra, and maybe if you fit each run and then average those fits, you would get, you know, a more clear power spectra that shows a difference between the frequencies. So,
yeah, that's a good idea. Yeah, this had crossed my mind. I was trying to figure out the logistics of how to do it, because basically you'd be taking all of the segments that you have, and then they all have frequencies, so you could kind of make those part of the problem as well, and then you can try to fit the specific frequency that you care about.
Possibly, yeah.
I
Possibly.
Is
was
that what you
about
were
to-
suggesting, or did I misunderstand?
You know, I would actually be sort of frequency agnostic as far as, I mean, I would just simply, you know the frequency you stimulated at, and just, do some sort of a linear interpolation of the power spectrum for each run, and then average those linear interpolations together.
I mean, one can get a wavelet window of the trial and average the wavelet windows too. That would be kind of in line
Yeah.
what you're saying. I mean, wavelet is kind of frequency agnostic, like you're checking all frequency band.
Yeah. Yeah, something that takes the whole, something that, right. I mean, right. I mean, I don't know if it would help, but yeah, it seems like you're throwing something away by looking at each frequency bin independently against the backdrop. I mean, it just against itself in some way. I don't know. It just feels like you're throwing something away.
Yeah. No, I agree. I think you're probably right. Another thing is that the GLM assumes that whatever the strength of that frequency response, it doesn't change over the 5 seconds. And that might be an assumption that is not very good for us, which one of the effects that I have noticed is that if I only analyze if I analyze all 4 runs of every subject, these are the results that we have. If I reduce it to 3 or 2 or 1, the results sometimes get stronger. And the first 2 runs seem to have stronger results. And I wonder if people kind of have a little bit of fatigue on this. Like they get messier and messier as they go.
That's another possibility. But one other thing to consider, and we're still looking at something different than EEG. And
yeah.
And I was struck by the fact that even though it wasn't convincing in terms of the frequency entrainment, when you did show the time frequency plots, when the stimulus went on, something happened almost immediately across all frequencies.
Mhm.
And so you're trying to make it one frequency, but it seems like something happened across all frequencies for all the different frequencies. And it happened almost immediately within 5 milliseconds. So
Okay.
I'm just wondering, that's like, I'm not sure, I can't even imagine how that could be an artifact. But it might be. Motion maybe, but if something, you hit something and then boom, all these frequencies appear in your MR signal when you give the stimulus, then that seems like something that I don't understand yet. And that's very different than with EEG, because maybe we are looking at something different than EEG.
Well,
There is a broad.
EEG also has a pretty broad onset kind of response. It just dies out very quickly. Ours, we didn't really see it die out very fast. So yeah, that's
Okay, so EEG looks at coherence, but we're not necessarily. I mean, we are looking at coherence to some degree, but yeah, I mean, I don't know. Yeah.
Tyler, hi.
Hi.
I can't remember. You did not use eye tracking, right?
No, we didn't use eye tracking.
So, but you have EEG simultaneously or not?
We did at 3T, we don't at 7T.
I'm very concerned about the blinking phenomenon. So,
About the what?
blinks. So, because you stick to this visual paradigm to explore very important, temporally difficult to assess domain of investigation, and you pay a lot of attention to stimulus delays, etc. Because, as you mentioned, people doze off, and like they may close their eyes, and also they blink a lot. So those blinking moments take, like, eye closure is around, like, say 40 milliseconds to almost 200 milliseconds, and pre-blink, post-blink eyelid closures will also blur some of the visual effects that you expect. So those moments may need to be taken out. But if you, for instance, in the future setup, it will be, I think, beneficial to use it. But if you have EEG, for instance, you can look at the frontal EEG channels and look at whether blinking happen, and those moments can be taken out from the analysis, because we blink a lot, like every couple of seconds, like we blink once. So this may induce a lot of bold signal fluctuations in the visual system.
Sure. No, it's a point well taken. When I have you stare at a 15 hertz checkerboard, you blink more than every few seconds. So, yeah.
Oh, that's right. So this task induces more blinks, right? Because eyes probably get, like retina gets more tired or whatever, like dry out. I don't know.
Sure. Yeah, no, it's a very good point. If there aren't any more questions, we're a few minutes over, but I am certainly happy to talk more if there are more comments. But thank you for coming.